Okay, good day, everyone. I'm Reginald Mercado from the Philippines. I'm from the industry. I run a company, an R&D company, for the past 26 years. We are developing devices from wired sensors, wireless sensors, and IoT devices. Did my screen change?
Yes, it changed.
Okay. So the outline of my presentation is IoT motivation for real-world applications, design and deployment of wireless sensor networks and IoT, and design and deployment of IoT plus TinyML. Okay, let's go to the motivations. These motivations are real-world applications. Philippines is surrounded by these countries in Asia. We're in the Southeast Asian region, and as you can see, there is a typhoon coming on this satellite feed from our weather agency. That was in 2009. It devastated the city of Manila. Really. Okay. And we are experiencing about 20 typhoons every year. And the Philippines is situated about 100 kilometers from the Philippine Trench and about 1,000 kilometers from the Pacific Trench. Okay. That's the reason we have different types of natural disasters waiting to happen. We have flood, flash flood, rain-induced landslide, storm surge tsunami, earthquake, water spout tornado, and volcanic eruption. Okay, these are events that happened in the past. Okay, this was in a flash flood in Ormoc in 1991, where 5,000 people perished. This happened in a single tragedy. Okay, caused by heavy rainfall of about 580.5 millimeters in 24 hours. And that caused landslide. Okay. Another event was in St. Bernard, Southern Leyte. Okay. Caused widespread damage of loss of life. It was a 10-day period of heavy rains and minor earthquake of magnitude 2.6, and the death toll was 1,126. Okay, these are just a couple of events, okay, disaster events in the Philippines. So according to WMO, close to 90% of all natural disasters in the last 10 years has been the result of hydromet causes. Okay. Only 10% is from geological and 14% from biological sources. Okay, anyone could be a victim of a disaster, okay, if you are unaware and unprepared. This is a picture of the Ginsaogon landslide, where 1,126 perished. Okay. To protect yourself, you should have the right information, the right plan, and you should have enough lead time. Okay. Early warnings are critical for natural disaster risk reduction and preparedness. So that's why during those times, we need to get information from the citizens. We conduct citizens interviews. We conducted radio propagation surveys. We installed initially rainfall gauges and water level gauges. So from this, we found out that the solution is a community-based disaster early warning system. So there is a need to implement hydromet data monitoring and early warning system. First is to warn the authorities and vulnerable population ahead of time of any threat of flood, flash flood, and landslide. Okay, to provide enough lead time between critical warning and completion of evacuation of lives and properties to safer grounds. Then number 3, to collect data about river system characteristics, about its rainfall intensity and water level over the years for research and creating mathematical models of the river system. Here's an example of a community-based flood early warning system model, wherein the basic system requires 3 stations: a rainfall station installed at the headwaters upstream, a water level sensor installed at midstream, and a data center installed at downstream near the flood-prone areas. Okay. Early warnings are issued to ensure enough lead time to evacuate. First, rain gauge station sends rainfall intensity data to data center. Okay, so this rainfall sensor senses the amount of rainfall hourly, then sends an alert information to the data center. Sorry. Okay, then the water level station sends alert level information to data center to indicate set condition. Then thirdly, water level station sends critical water level to data center as the go condition to inform the authorities to inform the population, the vulnerable population, to evacuate to safer grounds. The real test for my early warning system happened in June 2008, wherein Typhoon Frank transit over the St. Bernard region. Okay, so on June 20, it is about to enter St. Bernard, southern Leyte. Okay, it helped save 474 people. About 100 families were protected from a devastating flash flood caused by Typhoon Frank on June 20, 2008. Okay, so how do we go about that? So we need to design an IoT devices and its network. So we need to choose the best wireless technology for the application. Okay, we formulated that the best system for IoT should be low power, long range, and small in size. So this image shows a Semtech information about the different IoT network devices and its comparison. So you have the LoRa one, the narrowband IoT, the Zigbee, Wi-Fi, BLE, and 5G. And these are the range capabilities of each technology. Okay, from 5G, okay, up to LoRaWAN technology, which can extend transmission up to 15 kilometers. And this is the comparison between the power requirements of each technology, wherein LoRa provides the lowest power requirement, okay, compared to the other technologies. And if you need range or distance farther than 15 kilometers, you might as well implement a VHF to UHF digital radio that could send 256 bytes in 1 to 2 seconds. In the design, it would be best to implement programmable system on chip with dual core controllers and LoRa. Okay, you can use a PSOC 5 LP, a single core ARM Cortex M3 running at 80 megahertz, or a PSOC 6. It's a 2-core solution Okay, it has ARM Cortex M4 running at 150 megahertz and ARM Cortex M0 at 100 megahertz. And of course, you can use LoRa. In my implementation, I use the RN24A3, okay, capable of sending or receiving, okay, down to negative 148, okay, decibel for the input sensitivity, and capable of transmitting up to 14 dBm. It's a dual band LoRa. You can use the 43 megahertz or the 868 megahertz. Okay. And that would be a good candidate for Internet of Things TinyML solution. What are the benefits of designing your own IoT device? Okay. First is you can have customized design for optimized functions, system on chip or dual core. It could provide you with more power to do more with less, using only one chip, and it equates to lower hardware cost. It could provide you the benefits of introducing reprogrammability, which equates to flexibility, adding specialized software functions, lowers your overall systems cost, and the combined cost gives you or your system reliability, maintainability, sustainability, and gives you longer system useful life. Okay. This is an example of the PISOC 5 LP device I designed in 2014, wherein these are the sensors you can connect to the board, the different interfaces, the different power sources, memory storage, indicators, sirens, and buzzers. You can use different communication transceivers, VHF, UHF, LoRa, SMS, GSM, and ISM sub-gigahertz bands. This board was designed to be used for flood early warning system, landslide early warning system, tsunami early warning system, and other early warning systems, wherein this provides the hardware and software requirements. To share to you my 26 years of deployment, I started in 1996 using wired sensors, and I was able to install up to 1.5 sensors for different applications in the semiconductor industries. Then in 2006, I was invited in ICTP for a distributed laboratory instrumentation systems. This workshop focused on wired communications for sensors. Then in 2007, I started doing projects in wireless. In 2009, I was invited in ICTP wireless. And then 2015, my first encounter with IoT devices, the RN24A3. And during up to 2020, so we were able to install up to 2,000 sensors. Then for these applications, for disaster mitigation, environmental and research applications, for our National Weather Agency, different national government organizations, United and UNDP, and our current project is with the ASEAN IVO, wherein we are going to implement IoT and TinyML for the research project. Okay, these are samples of stations for the community-based flood early warning system. We designed the water level sensor, the rain gauge sensor, also this one, the GTek controller, also the GPS circuit, we designed it. And also the antenna, we designed it. Okay, ICTP was instrumental. ICTP wireless was instrumental for this design. Of course, we just buy these batteries, solar panels, and charge controllers. But we have currently we are designing our own charge controllers, and this was the VHF UHF LoRa, or you can use LoRa for the radio transmission. Okay. These are the different installations we had for the community-based flood early warning system. So this is the common setup for the rain gauge station. This is up in the mountains on top of the building. So you have a solar battery power source. You have the rain gauge. The instrument is inside this box, and you have the antenna. Same setup with this one. You have the box, rain gauge, and antenna. For the water level sensor, it should be placed or installed near the river system. So you also have the instrument box, the equipment frame that supports the box. Okay, you have the antenna and the solar battery power source. You have the water level sensor here installed and submerged in the water. For the data center, you should have the instrument box wherein the battery and instrument is installed, the antenna, solar is installed on the roof, okay, as you can see here, and a computer is installed in the community data center to collect and display the trends or the charts being collected, which represents the rainfall intensity and water level in the river system. This is the last project we did for United Nations Development Program, composed of four provinces: Bulacan, Rizal, Laguna, and Cavite. We installed about 34 stations, combined rainfall and water level stations, and their data centers. Shown here is the combination of using LoRa technology with VHF and UHF digital radios. Since the stations here are clustered near each other, it would be best to use LoRa technology because of its low power and long range. Then at this point, there is a data center which collects data from the stations, okay? The LoRa stations. Once these data are aggregated, they will be sent through a series of repeaters going to the National Weather Agency, okay, for analysis, data analysis, and flood early warning dissemination. This is an example of the display found on the data center computer. Okay, this indicates the rainfall, water level, early warning information, and the charts. Okay, as an example, these are the charts found in the SD cards of the unmanned stations. Okay, this is the rainfall intensity chart, wherein the blue is the 10-minute data, the red is the 1 hour, and the black is the 24-hour data. Okay, this is for the water level chart, okay, showing the effect of this rainfall intensity to the river system. Okay, the water level peak at 214 centimeters from about 50 centimeters. Okay, this is considered already a critical level that could cause a widespread overrun on flooding overrun on the town's streets. Okay, so these are the different levels: normal, alert, and critical. Okay. Another PSOC LoRa installation we had was in Bacoor, Cavite. Okay, so there are again 3 stations. Okay, these are the installation. We placed the LoRa module near the antenna to reduce transmission losses. Okay, through the transmission line. This is the battery. That's the controller. Okay, installation in the river system. Okay, data center. And this one is the landslide early warning system, wherein we again utilize LoRa technology, wherein this nodes monitors the cracks, okay, the moving cracks on the ground, sends the data to a gateway, and sends that the aggregated information to a data center in the town or city hall. Okay, view of the instrument and sensors. Okay, we also had the Buyog tsunami storm surge early warning system. We again implemented LoRa technology and PSOC, okay, in implementing this early warning system. Then we also had the environmental monitoring for San Sebastian Basilica, okay, to control the corrosion due to temperature and humidity. Okay. So initially we installed a wired inclinometers around the church. Okay. So we need to control humidity and temperature, okay, caused by rainfall. We installed about 14 LoRa sensors, okay, inside the church. Okay, these are the connections of the LoRa. Okay. Again, these sensors is ICTP wireless. So Dr. Marco was instrumental in the consideration of using these sensors. Okay, these are the installations inside the church. Okay. On the roof, these are the IoT node controllers. This is the gateway, okay, showing the sequence of nodes being received. Okay. And these are the charts, represents the temperature, humidity, wind velocity. And the last project we had there was installing different inclinometers and vibration sensors around the church. Okay, this will be using LoRa and PSOC. Okay, and lastly, I would like to present this. This was the I was invited by Dr. Nordin with this project, the ICANN IBO 2022 research project called P2IE Wealth. It's a physiological and psychological edge intelligence wearable health device, wherein we will design a wearable or wrist-worn device that could provide information on heart rate, SpO2, ECG, temperature, galvanic skin response, motion like walking, running, idle, free fall, single and double taps, temperature, humidity, air quality, and barometric pressure, and the location of the wearer. Okay, data will be sent via LoRa to a data center where the benefits will be this real-time remote patient monitoring method will provide medical doctors who are remotely located in the city the needed medical data while a patient is still in the danger zone or critical condition. This timely information would be helpful in assessing the health conditions and the preparation for the proper medical treatment for a victim. Okay, so this is the I was tasked to design the device. So this is the device I designed. It's a dual core Cortex M3 133 running at 133. This is a RP2040, which is supported by Edge Impulse. This is the GSR sensor circuit. This is the motion sensor circuit. This is the biosensor circuit, environmental sensor circuit. GPS receiver will be attached at these headers. The OLED display and LoRa will be attached at this point. Okay. This is the final PCB design. So we have here the MCU plus sensor. This is the front side. This is the communication board wherein we have the GPS. Wherein we have the GPS and a LoRa for 400 megahertz and a solar charge controller. The PCB layout, okay, for the front. This is for the back. We added several modules for the LoRa because to be chip shortage ready. Okay, so we have the LoRa 400 and 900. This is the RN2483 and RN2901 from Microchip, and the LoRa 800 900 from SID. Okay, connectors for the ECG, the back PCB layout. This is the our rendition of the final device, wherein you have the biosensing, display, casing will be aluminum, okay? Activity sensors will be inside, GPS receiver, environmental sensors, battery combo, and a capability of being charged by solar, and radio communication via LoRa, okay? This will be the operations. There will be different operations for Malaysia and Philippines. They have different LoRa bands. Malaysia will be operating on 900 megahertz, while we at the Philippines will be operating at 400 megahertz. It will be worn by elderly, pregnant, sick, and injured, and patients living in the mountains in near Chini Lake. Okay, a data center in the city collects near real-time data of health conditions. Okay, psychological, physiological, environmental, and location of a person wearing the device. Okay, this is for Malaysia setup, and this is for the Philippine setup, where it will be used for disaster victims and emergency rescuers benefit. Okay, the physical and the psychological and physiological information of the patients, okay, in an accident, okay, will be collected by the gateway, okay, as well as the health conditions of the rescuers, okay, conducting the rescue. Okay, and this concludes my presentation. Thank you very much.
Thank you very much, Reginald. Thank you very much. And there's a few questions in the chat. Well, one is about the LoRa coverage. LoRa coverage range. If you can comment on that.
With my previous projects, I was able to cover about 10 kilometers for the flood early warning system. But with this, for the P2IE, well, I think we could still cover about 5 kilometers for this. And we could extend the range if we're going to place repeaters. For example, in Chini Lake, if we're going to place repeaters at these points, we could still extend coverage up to 10 kilometers.
Excellent. Then was one kind of technical question about the Yagi antenna compared to the standard, I would imagine, omnidirectional one.
Well, for my flood early warning system, based on the design guides from ICTP, I prefer using the Yagi for the flood early warning system, and the omnidirectional for the devices, and Yagi for the data center.
Excellent. And then there was one question from our colleague at ITU in Pakistan about the, okay, he says, I want to understand its execution cycle from the business point of view. So when will it generate the alerts, and to who will receive the alerts, and then how it will execute to take actions on the physical environment?
Okay, which do you prefer, the flood early warning system or this?
Yeah, for example, yes.
Okay, for the early warning system, let's go back. Well, let's take, for example, this landslide early warning system. Okay. So this is event-driven. It means data about moving ground, the motion on the ground will be sent when the accelerometer is triggered by an event. Okay. Each sensor will send its data, okay, to a data center, okay, about 100 to 300 meters from the 5 sensor nodes. The gateway aggregates those data and send those data on a single transmission to a data center located about 14.4 kilometers, to a town center or city hall, wherein the data center is installed. At the data center computer, the data collected by the gateway are displayed on this computer, as well as the trends, okay, giving the authorities information if the vulnerable population living in the landslide-prone area needs to be evacuated. The lead time, okay, the lead time between transmission of a critical level or information up to the time the authorities gives the evacuation signal or trigger is very critical. So the system should buy more time, more lead time, to effect a safety evacuation of the vulnerable population to safer ground. Okay, that completes the cycle.
Excellent. And then there was one question from Apinung about the health application. And he was asking how many active users are there in the system, and is there a limit?
We are planning, we are targeting about 100. 100, okay? And probably in the latter part of the project duration, we will try to increase that to 1,000. To 1,000 users or 1,000 nodes.
Excellent. Okay. Are there any other questions for Reginald? No more questions. So round of applause. Thank you very much for the presentation. Extremely interesting. And
welcome.
The you know, social impact and the impact on local population is, you know, so big. It's really, really interesting. And I really hope I was thinking about this water level measurement where you showed the bridge and kind of the measuring line on the bridge. And I was thinking how TinyML could help in making sense of the water height. And yeah, and that how TinyML can play a role in these kind of applications. Excellent.